Hi everybody. So today I'm going to do the last part of this chapter, that is talking about capacitors. Last class I introduced capacitors, what exactly capacitor is, and these are the examples of these are the pictures of capacitors. So I've given you a different capacitors. All right. So look at here. This is a capacitor having a capacitance 4,700 microfarads, and the voltage is also given 35 voltage. You can apply at this much voltage. So these are the pictures of capacitors. All right. So just for your reference, I have given these pictures. So now today what I'm going to do is I'm going to do capacitor in a series combinations. Capacitor in a combination, right? How can I combine the capacitors? So before I do this, let's say look at here. I'll do a small recapitulations. We define a capacitor as a charge per applied potential difference. This is a very important formula for understanding a capacitance, and we also have said that capacitor does not depend on Q and V. It is a property of a capacitor. Capacitance is a property of capacitors. So therefore, it depends only on a geometry and medium within the two plates. So this is what I have. So these are the two very important formula as far as capacitors is concerned. All right. So now what I'm going to do is I'm going to do different combination of capacitors. All right. So we have two different combination of capacitors. Capacitor can combine in a series. All right. And capacitor can also be combined in a parallel. Right. So first I would like to start with a series combination of capacitors. So whenever we deal with the capacitors, we have two very important factors. Alright, two important factors over quantity those two quantities are the charge and voltage or potentials. So these are the two very important factors, right? Alright, so charge and potentials. So now I feel I don't need further explanation on series combination and parallel combination. This is very much done in lower class. Just for your better understanding, I say that whenever we talk about a series combination, series means I connect one terminal with another terminal, right? So I'll be having two capacitors. One terminal of a particular capacitor is connected to the another terminals of other terminal of another capacitor. So this is what I have C1. This terminal is connected to the next terminal of C2. The C2 terminal is connected to the next terminal of C3. This is what we call a series. So series means it is in a line. It is in a line, right? It is in a line. This goes straight, right? So this is what I have, right? So this is something like this. This is the right. This is right. Let's say this is left. This is left. This is right. This is left. This is right. This is left. This is right. This is how connected, right? Right over one capacitor is connected to the left of another capacitor. So this is where we talk about a series combinations. All right. And then one more understanding about a series combination is the positive terminal or negative terminal of one capacitor is connected to the positive terminal of another capacitor, and negative terminal of one capacitor is connected to the positive terminal of another capacitor. This is what we talk about a series combinations, right? And maybe again we will come across this kind of concept in a later class. So this is what I have. So let's say here in this case I have three capacitors having a capacitance C1, C2 and C3, and applying a voltage V, right? So what we are trying to understand is, what is the total capacitance. How to find out total capacitance. To find out total capacitance or equivalent capacitance. Alright. Or to find out equivalent capacitance. So how to do it is that, so I'll put one very important note, that whenever we put a capacitor in a series combinations, charge on each capacitor remain same. So that means Q doesn't vary. Q does not vary. Q does not vary. That means the Q remains unchanged. So this Q remains same. This Q remains same. All the Q on three capacitor remain same. Alright. And if a capacitance are very, if I say Q1, if C1 is not equal to C2, C2 is not equal to C3, then what is going to vary is voltage. This is very, very important, right? V or voltage across each capacitors vary. So now, if a voltage on each capacitor vary means it varies on what factors, right? So I say that it varies, right? The voltage across each capacitor varies, and if it varies, that means depend on capacitance. It depends on the capacitance. So the voltage on each capacitor is going to vary from one capacitor to another capacitor. The reason is that it depends on capacitance. It depends on capacitance. So this is what I have formula. This is going to be Q divided by C. Q remains same, right? This remains same. This is same for all capacitors. If I vary this, or if I change this, let's say if I vary this, if I change this, then V is going to change. Alright, and Q remains same. Alright, so that means this is the voltage across each, I say, individual capacitors. Alright. So now let's say what about V1? V1 is capacitor of first capacitor. V1 is going to be Q by C1. What about V2? V2 is going to be Q by C2. What about V3? V3 is going to be Q by C2. These are the different. And what about total voltage? Total voltage applied here. Total voltage applied must be equal to. This is very important, right? Whatever voltage you apply are all consumed by all the capacitors, depending on capacitance. Alright? Whatever voltage you apply is being consumed, is being taken by all the three capacitors, depending on its capacity. Now let's see whether if a capacitor is high, whether you take more voltage or less voltage, that you will see, right? So this is what I say. So now I say V1. How much is V1? V1 is going to be Q by C1. So look at it. If a capacitor is high, then voltage is going to be small. If a capacitor is small, then a voltage is going to be more. Alright, this formula tells you, right? So this is equal to C2, this is equal to C3, which is equal to V by Q's, I take commons. This is the point, right? And now the point is, what is V by Q? So V by Q is nothing but 1 by C equivalence. This is what I have. So this is a total capacitance. This is the total capacitance. This is the total capacitance or equivalent capacitance. So the equivalent capacitance in a series combination is, say that the reciprocal of equivalent capacitance is equal to sum of reciprocal of its individual capacitance. Alright? Reciprocal of equivalent capacitance is equal to sum of reciprocal of its individual capacitance. Alright, so I'm going to write here, this is going to be 1 by C1 plus 1 by C2 plus 1 by C3. So therefore, I can rewrite this equation saying that this equivalent, this is going to be reciprocals, alright, C1 plus, C1, C2, C3 divided by C1 plus C2 plus C3. This is what we have. Why? Because how I arrive at this point is that, I'll tell you this, alright, I'll take the LCMs. I'm sorry, this is wrong. I'll take LCM. LCM is going to be C1, C2, C3, C2, C3 plus. This is going to be C1, C3 plus. That is going to be C1, C2. This is what I have. And if I reciprocal it, what I'm going to get is, if I reciprocal it, what I'm going to get is C equivalent is equal to C1, C2, C3 2 divided by C1, C3 plus C1, C2, C3, C1, C3, C1, C2. This is the point. Now, if I have a two capacitance, then this is going to be very simple. This is going to C1, C2 divided by C1 plus C2. This is for two capacitance. This is for two capacitance, and this is for three capacitance. Alright. So therefore, equivalent capacitance is going to be smaller than the smallest of its individual capacitance. Alright. So now equivalent capacitance which I obtain could be smaller than the smallest of its individual capacitance. Alright. So this is one very important. The charge remains the same all along the capacitors, and the voltage is going to vary. The voltage varies based on its capacitance. So this is for series combinations. Alright, now I will do a parallel combinations. So parallel combinations. This is what I had. This you can do as a home assignment, right? You can take this, right? So I'll be giving a series combinations. This is a 1 farad, 0.1 farad, 0.1 microfarad, 0.2 microfarad, 0.3 microfarad, and you are supposed to find out a voltage. And just to see, you find out how much voltage must have been, and voltage is going to be divide. They say voltage is going to be, total voltage is equal to V1 plus V2 plus V3. Alright, this is the voltage. And what about charge? Right? Charge is going to be C multiplied by V. How much is C? This C refers to our equivalent capacitance. This C refers to an equivalent capacitance, right? So you find out as a home assignment, right? So this, how you are going to get this C equivalence? Alright, C equivalent 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3, and you are going to get it. Once you get this, what is V? V is going to be a 12 volt, and you get a Q. Once you get Q, then how much is V1? V1 is going to be Q divided by C1. And C1 is given, this is given. What about V2? V2 is going to be, this is C2, everything is given. And what about V3? Q divided by C3, everything is given, you can easily find out. Alright. Okay. So this is, you do it as a homework. Alright, now what I'm going to do is, I'll do a parallel combinations. So, this is parallel combination. Whenever we talk about parallel combinations, so, you say that the combination is said to be parallels if two corresponding sides, the two sides, right? Capacitors are joined, right? Corresponding sides of capacitors are joined. Corresponding side, I say this, if I say this is left, this is right, this is left, this is right. Left joined with that, the corresponding left of a C is C1 is C1 joined with the corresponding sides of the C2, and then joined with the corresponding side of C3, and the corresponding side of C1 joined with the C1, right? One terminal of C1 joined with the corresponding terminal of C2, then corresponding terminal of C3, and this kind of combination is what we call as parallel combinations. So that means both sides of the two capacitors are joined correspondingly, right? That means, and the other way of understanding a parallel combination is if the positive terminal of one capacitor is joined with the positive terminal of another capacitor. Alright? If a positive terminal of one capacitor is joined with the positive terminal of another capacitor, and then we call this combination as parallel combinations. Look at here. All the positive terminals are joined as one terminals. All the negative terminals of the capacitors are joined as another terminal, and this combination is what we call as parallel combinations. Okay. Now again, our objective is to find out equivalent or total capacitance, right? Total capacitance or equivalent capacitance, right? This is to find out equivalent capacitance. Again, same procedures, two important factors for capacitor. One is charge, another one is potentials. Now in case of parallel combinations, charge remain, the potential remain same across all the capacitors. Potential difference over voltage remain same for all capacitors. That means V1 is equal to V2 equal to V3, which is equal to voltage you supply. And what is going to change? What is going to change is the charge. Charge on each capacitors vary, and I say it depend on its capacitance. Depending on the capacitance, charge is going to vary on each capacitor. So capacitor now, in case of series combinations, the capacitor that decides voltage. Now in this case, it is the capacitor which decides the charge on each capacitor, right? Charge on each capacitor. So this is the Q remains same, and how it is going to decide is this Q is equal to CV, and this remains same and this is going to change. If this changes, then Q is also going to change. If this changes, then Q is going to change. This is very, very important. Alright. Now what I'm going to do is, what about charge on capacitors Q1? A charge on capacitor Q1 is going to be C1V. Charge on capacitor 2 is going to be C2V. Charge on capacitor 3 is going to be C3V. And what about total charge? When I say a total charge would be going to be Q1 plus Q2 plus Q3. Total charge on our entire system is going to be a sum of all the charges, right? So Q1, Q2, Q3, right? So therefore, how much is going to be Q1's? And look at here. If C1 is more, then charge is going to be more. For applied voltage, this is the definition of capacitance, right? If a C1 is more, then Q1 is going to be more. If a Q2 is less, then Q2 is going to be less. I mean, if a C2 is less, then Q2 is going to be less. If a C3 is more, then a more charge on capacitors C3. Alright. So therefore this is going to be C1V plus C2V plus C3V. Okay. Then now it goes down, Q by V is going to be C1 plus C2 plus C3. And this is the total charge. This is the total charge, and this is the potential applied, potential difference applied. Alright, and then this is going to be, therefore, this is going to be C equivalent. C equivalent is equal to C1 plus C2 plus C3. So I'm going to write here equivalent capacitance is going to be C1 plus C2 plus C3. This is the final answer. So total capacitance or equivalent capacitance is going to be sum of its individual capacitance. So that means the equivalent capacitance is more, alright? It's going to add up, right? So equivalent capacitance is going to be sum of its individual capacitance. So again, I'm going to do a small recapitulations. So in this case, and potential difference or the voltage across each capacitor remains same, and what is going to vary is if Q is going to vary, and depending on C, alright, Q is going to vary. If a C is more, Q is going to be more. If C is less, Q is going to be less. So this is the point. Alright. So this is what I have. Very important. So the equivalent capacitance is going to be sum of its individual capacitance. So this is all about combinations. Alright, parallel combinations. And then again home assignments. Alright, same. I connect this in the parallel combinations. Now here voltage remains same. Now, here what you are supposed to find is, you are supposed to find out a charge. Here, better I say a charge. I'm going to say a Q1, I'm going to say a Q2, I'm going to say a Q3. You are asked to find out what is Q1, what is Q2, what is Q3. So this you are going to find out. Alright. Charge remains same. This is home assignment. Don't put I1, I2, I3. Okay. So you are asked to find out what is the charge on each capacitors. Q1, Q2, Q3. Okay. The same. Alright. Very simple. Q1 is going to be C1 V1 V, and Q2 is going to be C2 V, and Q3 is going to be C3 V. Same? Alright. You substitute, you get it. Just do it as a homework. Alright. Now I'm going to do a last topic of this chapter, that is energy stored in a capacitance. Energy stored in a capacitor. And I told you that last time. If I have a capacitor, if I apply a potential difference, there will be a potential difference across the two plates. Then there will be electric fields. So that means the capacitor store a charge, and due to which it has a potential difference. It has the electric fields. Alright. Once it has the electric fields, it stores the energy. So capacitor is the one important job of capacitor is to store energies. It stores the energy, right? So now we would like to find out how to find out energy stored in a capacitor. How much energy capacitor could afford to store? Alright, so this is what we are going to do. So our objective is to find out energy stored in a capacitor. Energy stored. Objective is to find energy stored in a capacitor. Energy stored in a capacitor. And now, very simple to find this. Only concept that you require is initially, let's say start with this. Initially, I have two plates, electrically neutral plates, and what I do is how much energy is stored in the capacitor of a charge plus minus Q. Alright, plus minus Q. One plate will be having a plus Q, other plate you will be having a minus Q. This could be a plus, this is a plus, right? So this is as simple as saying, right? This is the simple, right? This is in a very simple word. We can say that how much work is required to transfer a charge from one plate number 2 to plate 1. I go on transferring a charge from positive charge, right? Small positive charge. This is not practical. This practically is not, it is not practical, right? You can't do in a lab and then transfer charge. It's not at all practical. But for hypothetically, I can say that, we can say that I transfer a positive charge from one plate to another plate, go on transferring until I get plus Q at this side and minus Q at that side. I go on transferring a small Q from plate number 2 and then transfer it to a plate number 1. If I transfer a positive charge from 2 to plate 2 to 1, 2 remain negative, 1 remain a positives, and go on transferring until this plate remains negative, this negative Q, this plate remains positive Q. This is how it is. So we are going to find out total work required to transfer charge Q from plate 2 to plate 1. Alright, job is to find out work required to transfer. So what we are going to find is, so this is our objective, to find out work required to transfer plus Q from plate 2 to plate 1. This is what we are going to find out. This is to find out work required to transfer plus Q from plate 2 to plate 1, and amount of work required is stored as potential energy. Right? So this is what I have. So what I'm going to do is I consider a capacitor. Let's say I have a capacitor of capacitance C, area A, and then let's say a medium is a vacuums, and the distance of separation is V is the distance of separation. So this is what we are going to do. So now what I'm going to do is, let's say this is, I'm going to transform, let's say this is prime, this is primes. So this is intermediate states. I take the intermediate states where charges are plus q minus q. Alright, this is the intermediate states where the charges are plus minus q prime. Alright. So why I take the intermediate state is that now once you take this, what I'm going to do is I bring a small positive charge from plate 2 to plate 1. This is a plate number 2, this is a plate number 1, this is a plate number 2, this is a plate number 1. Alright. So how much work is required to transfer small delta Q prime from 2 to 1? First I will find this. Once I found this, then I integrate this. Alright. So now the point is, let us take intermediate state where charge on capacitor is plus minus q primes, and the potential is voltage is V primes. Voltage is V prime. Alright. And now I say that work required to transfer a small delta Q prime plus small delta Q prime from plate 2 to plate 1 is given by how much work is required. Work is given by potential, right? This is a potential Q prime. I say, what is the potential? I give the potential is V primes. Alright, V prime is, I can define something like this. V prime is work required to transfer unit charge from 2 to 1s. I can define this as work required to transfer unit charge, unit positive charge from 2 to 1. This is the definition of V primes. So what we can transfer delta Q prime from 2 to 1 is given by this. This is. Now what I'm going to do is, what is Q prime? What is V prime? V prime is given as, what is V prime? V prime is given by Q divided by C, right? This is why, because C is a Q prime divided by C. C is a capacitance and Q prime is a charge. So I substitute. This is going to be a small work. I'm sorry. This is small work. This small work is going to be Q prime C D primes. Alright. Now my job is to find out what we can transfer Q plus Q from 2 to 1, right? So now my job is to find out look at here, I love this. Now my job is to find out Q, right? So W is the work required to transfer plus Q from 2 to 1 is given by look at here, this is how I integrate 0 to Q, and I integrate this. This is how we do integrations. Q prime dq prime divided by C, this is dq prime. Alright, so which is given by 1 by 2c q prime square, limit from 0 to q prime, q. Alright, now this is going to be, I integrate this, so this is equal to q square divided by t minus 0. So the work required to transfer q from 2 to 1 is going to be given by this. This is very important formula. This is very, very important formula. Alright. So this is the work, and this work is stored as potential energy. This work is stored as potential energies. So therefore I just say work is stored as, this work is stored as a potential energy, stored as potential energy. Therefore potential energy would be C. Alright. Now I'll write in other terms. Alright. What is Q? Q is equal to CV. Alright. So therefore U is going to be C square V square divided by 2C. Cancel out. You will get half CV square. This is second formula. This is the second formula. And again, I can write like C is equal to how much, right? C is equal to Q by V. Therefore, U is equal to Q square divided by 2. Q by V. Q cancel out. 1 by 2 and Q V. This is the third formula. This is the third formula. So I'll be having a 3 different formula. Alright. So that means I can represent this formula in terms of charge, capacitors, capacitance and potentials. The first formula is going to be, half CV square. This is the second formula. First formula is going to be U is equal to Q square divided by 2C. Second formula. And third formula is going to be, these are the 3 different formulas. They are, all the 3 formulas are one and the same. The only difference is I represent in terms of C and Q, I represent in terms of C and V, I represent in terms of Q and V. Alright. Now what I'm going to do is, let's try to figure out energy stored in terms of electric field. Energy in terms of electric field. So we'll try to figure out energy stored in terms of electric field. So this is what I have. What is capacitance? Capacitance is given by epsilon naught A by D, and we know that electric field inside capacitor is going to be sigma by epsilon naught. This is one more, and we know that sigma is equal to charge density Q by A. Alright, so now to figure out this, now we know that, let's say we know that Q is equal to V, potential energy is equal to Q square divided by 2C. How much is Q? Q Q is going to be sigma A whole square and 2, and what is C? C is going to be epsilon naught A by D. Alright, so having this, I rewrite this formula, sigma square A square divided by 2 epsilon naught A divided by D. This A cancel out. U is going to be sigma square 2 epsilon naught A, D goes up, cancel out. This is what I have. Now what I'm going to do is, I will do this square so that epsilon comes at denominator. Why I do this is, E is equal to sigma by epsilon naught. E is electric field. Alright, E is electric field. This is what I have. Alright, so therefore, energy in terms of electric field would be equal to, this is electric field, epsilon naught AD. This is potential energy in terms of electric field. This is a potential energy in terms of electric fields. This is a potential energy in terms of electric fields. Now what I'm going to do is, what about potential energy density? This is small q is potential energy densities. Potential energy density is defined as potential energy per unit volumes. This is not a voltage, this is volume, right? This is volume, right? Potential energy density is a potential energy stored in a given volume, right? So this is given by half E epsilon naught AD. AD is a volume, cancel out. This is what I have. Alright. This is potential energy density. This is a potential energy density. Alright. So now I have done with the potential energy, and then potential energy in terms of electric field, and finally we arrive at potential energy. And this is the property of capacitors. This is the property of capacitor with the given applied potential difference or with the given electric field. So now what I'm going to do is, the last is, what about the effect of effect of dielectric? What about the effect of dielectric? This is what I'm going to do now. When I put a dielectric, when I put a dielectric, what happens is that epsilon becomes K epsilon naught, and electric field become this. This is for disconnected cell after charging, right? I write here disconnected battery after charging. Alright, so this I say U is going to be half, alright, half, and then what I have here is this, right? Half this all on volume, right? E is going to be 1 by 2. I'm sorry, this is E square, right? This is E square, right? Alright, this is E square, right? Why? Because we have this. I'm very sorry. This is going to be, what I have is 1 by 2 sigma square epsilon naught square AD. This is going to be E square, right? So therefore this is E square. So I've done a small mistake. Alright. So this is E square. Alright. So E square means this is going to be E K square. Then what about this? This is going to be K epsilon naught AD. And this is K cancel out. E. Alright. This is going to be epsilon A divided by K. This is going to be alright. This means that energy is going to decrease. If I insert dielectrics and battery is disconnected after charging, then potential energy is going to decrease. Potential energy is going to decrease by 1 by K times. K is the dielectric constant, right? Now next I'm going to do is connected capacitors, battery remain connected, battery remain connected, battery remain connected, battery remain connected after chargings. Battery remain connected after chargings. So if a battery remain connected after chargings, epsilon become K epsilon naught and E remain E naught. Why? Because electricity doesn't decrease. Why? Because you keep on charging, right? And then what about potential energy, right? Potential energy would be, this remains same. Alright, this remains same. K epsilon naught Kg, and this is going to be K U naught. So therefore, finally I get K U naught. If I keep capacitors, if I keep battery connected, then energy is going to increase. Energy is going to increase by K times. So you may confuse these two, right? In example, if they say that if a capacitor, if a battery remain connected, what is the effect of dielectric on an energy means this is a. And if a battery is connected, then this is the effect. If a battery is disconnected after charging, and what is the effect of dielectric on the energies, this is going to be an effect of. So this is very important, and you may confuse. All right. So therefore, you have to be little careful, right? So therefore, I have written this. In your textbook, it is not written like that. So maybe in the exam they may ask, right? So with this, I have finished entire chapter number 2. Thank you.